Our next speaker is Mr. David Burlingame. David is the principal with Electric Power Systems Incorporated. David's going to speak to us a little bit here. David, off to you.
We're going to talk about energy storage here. I don't think you can really stress the importance of energy storage in an islanded power system, especially in an islanded power system that's moving towards renewables. And not just renewables. I think the important thing to point out here that all of these renewables that are being discussed today are variable renewables, not just renewables, but variable renewables. So I think it's important for the power system to make plans in order to be able to sustain that renewable growth. And I think that's what GPA has started to do. And they're going to be well ahead of where some of the other neighbor islands are. Okay, next slide. So we did a project for GPA, and we're talking about the energy storage project. And some of the goals that GPA laid out when we started this project was they wanted to ease renewable generation integration. They wanted to make it easier to integrate renewables. And that's something that sometimes a lot of the people that are actually installing the renewables don't really realize how difficult it is for the utility to handle renewable growth. It's something that takes a lot of planning and a lot of forethought. And as you can see with some of the slides on the Hawaiian Islands, there's some issues there that are going on there that are extremely difficult to deal with if you don't get out ahead of the game. Want to increase reliability and the power quality. Want to increase spinning reserve. Spinning reserve in an islanded utility is a huge component of cost. And as you add renewables, that spinning reserve cost can actually increase a lot. And so one of the things that GPA wanted to do was be able to decrease its spinning reserve costs while at the same time adding renewables. They wanted to improve production costing. And we looked at this as a two-phase approach. We looked at it initially a 40 megawatt energy storage project, and then the second phase was trying to see what our performance assessment and system requirements were. Okay, next. So what are the applications for energy storage? One of them is regulation, and this is the one that I think is probably the easiest to grasp. What regulation means is that as you put on a variable renewable generation, particularly solar, solar is a great product. It can have a lot of benefits to the system, but it also is probably one of the most dynamic power sources that are on the power system. So what does that mean to the utility? What that means to the utility is that they have to react to changes in their system load that they've never had to react to before. So they may have, as you add renewable generation, in a system like the GPA system where they may have had a load growth in the order of maybe a couple of megawatts a minute at their maximum load growth. That may be 3 or 4 times that when they start adding renewables. And how they deal with that is a huge issue. And so regulation, that's what's called regulation, is how you deal with the changes in your load. The transient response, this is one that is a very big problem in the Hawaiian Islands. It is a problem that you need to be able to deal with proactively. What the transient response means is that as you put on PV, not so much large plant PV like we've seen here today that GPA is putting on, but as you put out distributed rooftop PV, that PV can increase the utility's contingency. And what's a contingency? The contingency is effectively how much generation can the utility lose at one time. So what distributed PV looks like is it looks like, from a system point of view, it looks like one generator. So on the Hawaiian Islands, for instance, they've increased their contingency on some of the islands by 5 times. So now they're having to cover 5 times the largest generator to cover the loss of the PV. So that's an issue that GPA is trying to get out ahead of and trying to look and see what they can do to minimize that. The primary considerations are megawatt and megawatt hours. That's basically a capacity issue. John Benavente talked about that GPA's issue in this regard right now is a capacity issue. Megawatt hours is how long you need to hold that capacity. And the last one is what technology or options are available once you decide that. Okay, next. From a practical consideration, what do you have to look at? Installation costs, O&M costs, performance criteria, state of the technology. There's a lot of technologies out there that are really developing, and I think maybe in a few years they might be there. But right now, you need to look and see what's real and what's Memorex. And all the old people got that one. What's the availability in the market? And what's the dynamic market? Especially in energy storage, there are several large energy storage projects. I know that, we're working on an energy storage project in Alaska. That's where I live. That's a 200 megawatt energy storage project. That's a combination of batteries and flywheels. Well, to give you a feeling for it, currently, a 200 megawatt battery storage project would take just about all the battery capacity of the world to make and get it installed in that construction period. So you need to look at the dynamic market, because projects that are going on as they exist today have a big impact on what you're going to be paying and what's available. And hopefully, I think, like Jeff said, that battery technology is just changing in a very, very rapid manner. And I think that you're going to see the benefits of that. But right now the technology's there, but the battery production hasn't kept pace with the technology, to be honest. Okay, next. Okay, existing GPA has about 1.3 megawatts of distributed PV capacity. Phase 1, they're going to add 25 megawatts of plant PV and 10 megawatts of wind. That's an important distinction. 25 megawatts of plant PV is considerably different than 25 megawatts of rooftop PV. 25 megawatts of plant PV, they're pluses and minuses, but 25 megawatts of plant PV has a lot different system characteristics than 25 megawatts of rooftop PV and 10 megawatts of wind. Phase 2, this is what they're estimating. In addition to this, they want to add another 50 megawatts of plant PV and 45 megawatts of distributed PV. Okay, next. This is the performance criteria. This is the biggest driving factor in energy storage for an islanded power system. What kind of reliability are you going to live with? This is the single biggest determination of what your battery storage is and what your battery storage costs are going to be. At GPA, we actually looked at several things, but they actually decided on a criteria that they will allow one stage of under-frequency load shedding for a single contingency. That's a big issue. It's one right now, to be honest, that the Hawaiian Islanders are dealing with. The Hawaiian Islands are dealing with, historically, one of their islands on Oahu. They have never had load shedding for a single contingency event. They had a single contingency event this year that went through 4 stages of load shedding because of renewable energy. So, they are now working on the criteria, but they're working on the criteria behind the 8 ball, whereas GPA is trying to get in front of it. So this is a huge issue. This is the first bullet there is the biggest issue of the whole study. What is your reliability criteria? And that drives everything. The next one, which is a huge issue in terms of cost, is what are you going to gain with that battery? What are you trying to do? And the other one is they're trying to limit their spinning reserve to 15 megawatts. Currently, or maybe I should say not currently, historically, GPA has carried as much as 46 megawatts of spinning reserve over peak to cover their largest spent single contingency, which is the loss of the Cobblers unit. Cutting it down to 15 megawatts is a risk, and in combination with the battery, they will take that risk and they'll say, okay, over peak, if we have an outage, we'll allow one stage of load shedding. It's a huge balance between what's acceptable and what's unacceptable and the costs associated with it. No daily unit cycling. This is their large thermal generation units. The maximum size we wanted was a 40 megawatt energy storage. That's not the maximum size we wanted. That's the maximum size that we thought was economical for the GPA system. Some of the energy storage additions that we've heard today, if they come about, this battery will need to be increased, or the storage system will need to be increased. But for the system as we envisioned in our study today, this was a good size. And our goal was that we wanted the batteries or the energy storage to last 15 minutes. Why 15 minutes? 15 minutes ties in with the allowable single stage of under-frequency load shedding. If you go through under-frequency load shedding and you only have 15 megawatts of spinning reserve, you can't restore your load to your customers without starting a generator. So the big issue was, how long are your customers going to be off? GPA said they don't want their customers off any longer than it takes them to start one of their fast start units. That's why the 15-minute storage was there. The length of the energy, how long that battery has to put it out, is a huge determination of cost. Next. So, primary options, storage technologies. For this system, there's really only two technologies that are available: batteries and flywheels. Now, within each of those, you're going to have different types of batteries, you're going to have different types of flywheels. But there's really only two technologies that are currently available and in production today. Other technologies like compressed air. Compressed air is like a big storage tank you put through a gas turbine instead of gas. Pumped hydro and thermal. Not really applicable. There's a couple of demonstration projects for compressed air, but nothing that we'd really want to put out as a commercial item. So batteries and flywheels are the issue. Okay? Next. This kind of gives you an idea of where you are. In the world of energy storage, it's dominated by hydro, right? Pumped storage hydro dominates the storage market. You can see as you go into this, flywheel, batteries, compressed air, and thermal. In an islanded system, you're seeing more and more applications of batteries and flywheels. We have a small system in Alaska. It's about 26 megawatts. It soon will be 100% renewable. 6 megawatts of wind, 3 megawatts of batteries, 2 megawatts of flywheels, and 20 megawatts of hydro. It's a pretty state-of-the-art system. It's a combination of flywheels and batteries. Next. This is the position of energy storage technologies. This is what we talked about before about how long the energy needs to be available, 15 minutes, as to what technology is there. You can see if you need to go out for the area for minutes, 15, 20 minutes, there's really only batteries, storage, hydro, and some flywheels. 15 minutes for a flywheel is really at the extreme edge of a flywheel. I know that they say that that you can do it, you can actually do it, you can parallel the flywheels and get that out there, but it's a huge cost. Flywheels have a lower life cycle cost than batteries, but they have a huge installation cost. Okay, next. Although I got to say that's coming down. In fact, I think one of the companies out of Australia is probably one of the leaders in driving down the cost of flywheel technology these days. So what are we trying to accomplish with energy storage? This is what you're trying to replace, the governor response. So in the power system today, GPA is all thermal generation. And what a governor does, it looks at the power system frequency at 60 hertz. If the system frequency is not 60 hertz, the governor is the accelerator or the decelerator that changes the generator's fuel supply to tell it needs to go wherever it needs to go to get to 60 hertz. As you move towards a new generation regime and you're taking away your regulation and your reserve margin, something needs to take the place of that governor storage, right? Because you reduce the number of units that you're operating. So something needs to take the place of that governor response, and that's stored energy. Regulation. These are the two issues, and these are the two, right now, the two opposing technologies within the battery market. Regulation, which is a continual charge and discharge. Whether it's solar or whether it's wind, you'll notice when you start putting that on your system, your frequency is no longer this, it's this. And that continual up and down of 60 hertz, going away from 60, going down to 59.6, going up to 60.6, is called regulation. The requirements of that regulation are much different than the next one, the reserves regulation, where you trip a unit and all of a sudden your frequency goes like a rock from 60 down to 59, and your batteries have to give all they have to bring the frequency back to 60 hertz. Those two requirements, one's called a deep discharge cycle, the reserve requirement. One's called a continual charge discharge cycle. Those are two different battery technologies. Currently, that requires a hybrid battery system. Now, there are people trying to make that where you get one battery that can do both things. But currently, what's on the market today, if you want to regulate frequency, you get one type of battery. If you want a deep discharge, you get a different type of battery. So in an island condition, in an islanded system, it's difficult because you need them both. So this is another application where, you know, it may actually be good for a hybrid system. The system I was telling you about in Alaska, that's about a 20 megawatt system, they started out with a 2 megawatt battery that was designed for deep discharge. But because of the variability of the wind, their battery life started degrading so fast that they've decided to put in flywheels to take care of the regulation and then save the batteries for deep discharge. The next one is load shaping and demand control, which is I think John Benavente talked about earlier. It's trying to shift your energy to a cheaper period of time. Okay, next. Flywheels, kinetic energy, spinning mass. You know, in the old days, what flywheels were was you would take something like a big motor, put a big weight on it, connect it to the power system, and that's your flywheel. Okay? So your flywheel would essentially be an old generator or something that you put a big weight on, and that big weight is what kept the system from from changing from 60 hertz. All a flywheel is inertia. I mean, if you think about it that way, if you have a motor turning at a certain RPM, that motor turns at the same speed as your power system. So if your power system's spinning at 60 hertz, your motor turns at 60 hertz. If your power system all of a sudden goes to 59 hertz, your motor, because it's a big weight, doesn't change to 59 hertz. It still tries to spin at 60 hertz. Since it's still trying to spin at 60 hertz, it helps prop up the power system. That's really all a flywheel is. The new flywheels are way complicated. They're in a vacuum. They're in 250 kW blocks. They spin at anywhere from 2,000 to 30,000 RPM. They're all electronic controls. But the basic premise is the same. They're just a weight that's spinning in a circle that's propping up the power system. Okay, next. This will kind of give you an idea of what the size of the projects from a flywheel point of view. This is from the DOE thing. Right now the largest capacity that's there is a 20 megawatt. Longest storage capacity is about 15 minutes. And the 20 megawatt, 15-minute battery, flywheel costs about $43 million. Pretty expensive today. Next. Batteries. Batteries have been around for a long time. In Alaska, we've successfully used batteries on a number of installations. We used to have the largest battery installation in the world for many years. We have a 40 megawatt battery that's designed as a deep discharge battery. Its improvement in the Alaskan grid is just immeasurable. I mean, when that battery is out of service, everybody knows it. But they have a high life cycle cost. That battery system is about 10 years old now. They're starting to replace batteries. They're starting to replace strings. It is an expensive system to maintain. It is, but its costs, its benefits are huge. Okay, next. Like we talked about before, the variations in battery technologies. As you define what your energy requirements are, that's going to point you to what your battery technology is going to be. And what, to be real honest, what you would probably do is you would probably define your energy requirements and let the battery manufacturers define what the battery technology is. I mean, those guys are way more attuned to battery, what's currently available and commercially available than anybody else. So, define the requirements and let them meet them. Okay, next. This kind of gives you an idea of battery projects through DOE. Largest capacity is 40 megawatts. Longest storage capacity is 8 hours. 40 megawatts costs you about 47 to 58 million. We actually have several projects, like I said, in Alaska. Alaska, for those of you who don't know anything about it, is operated as electric islands. Other than a few areas, most of all of our generation is all fuel oil based. So everybody there is scrambling on wind, batteries. We don't have much solar, but wind and batteries in combination with diesels. We have a couple of utilities which are experimenting with 100% wind with batteries. So the Alaska system is pretty far advanced in that world. Okay, next. So what do we do on GPA? Phase 1, 40 megawatts. They went through a lot of studies on this, a lot of determinations, loss of the largest unit. And the biggest issue, I'll stress again, is what's acceptable criteria for your reliability. When we actually set the criteria for if you don't want to have any load shedding for your loss of your largest unit, the BES went up to 65 megawatts. Pretty huge increase, 50% increase in load for just that one criteria. Okay, next. Unit outages, so this kind of goes back to what we decided on. So we're going to use it for unit outages, frequency fluctuations, although that's going to be at a cost, and the technology considerations are lifetime and depth of discharge. Okay, next. Does a 40 megawatt battery meet everything? Almost. In the GPA system, like most islanded systems, you have to put up with more things that a utility in the mainland does not. One of the things that happens is that on the mainland, when you have a fault on your transmission system, and by a fault we mean a tree falling in the line or the line falling on the ground. In the mainland, when you have a fault like that, the frequency stays constant at 60 hertz, right? Your voltage may change, but your frequency stays constant. In an islanded system, that's nothing but a dream. So what happens on these, when you have faults in your transmission system, you have a big swing in voltage and a huge swing in frequency. And this battery cannot handle all of the swings in frequency and voltage on the GPA system. There are a few cases where it doesn't. Renewable ride-through requirements. This is a big deal. This is a huge deal that Hawaii is fighting. And it deals primarily with both plant, station PV, station wind, distributed PV, and distributed wind. Almost all the PV in Hawaii was installed in accordance with IEEE 1547, which is kind of the standard in the mainland. IEEE 1547 was adopted not to protect the utility, but to protect the distribution system. And there is a huge difference in that. Because what they were trying to protect is if you have a bunch of PV on a distribution feeder, and that feeder suddenly opens because it's disconnected from the power system for whatever reason, if that PV doesn't trip offline, you get a lot of very damaging voltages and frequency on the distribution feeder. So IEEE 1547 was adopted and formulated to try and protect the distribution customers from that damage. In an islanded system, the system requirements are in direct opposition to the distribution feeder requirements. Because the same problem that you want the distribution system, the distribution PV to trip off for, from the system point of view, you need it to stay on for. So in the Hawaiian Island system, one of the things that is happening is that they have distributed PV. On the island of Oahu right now, they have 350 megawatts of distributed PV. All of that PV will trip offline if the frequency goes to 60.5 hertz. All of it. So you have a utility system with a 900 megawatt peak that can lose 350 megawatts of PV. Was the system planned for that? Not even close. So one of the things as you're moving forward that you need to make sure you pay attention to, and it really comes in with storage. One of the answers for the Hawaiian systems is storage, is what do I want my systems to ride through requirements to be, because it is a huge issue. We found that there is a minor sensitivity location where it's where you put the storage, but not a big one. You can basically put it anywhere. The 115 kV system is a little bit better than the 35. And we didn't see that the battery really needed to provide any voltage support for the system. Okay, next. This just kind of gives you an idea of what we've been kind of talking about. The red line, what you're looking at here is a simulation. There's no red here, right there. What you're looking at is a simulation. If you look up on the left-hand side of the plot, where they both start out as a straight line, that's 60 hertz. Okay, so that's what you want your power system to look like. The black line is what happens if you trip a generator to the frequency with energy storage. And you can see you go down to 59 hertz, and you come back up, and you will eventually recover to 60 hertz. The red line is what happens if you don't have energy storage. You can see you trip a generator, you go down. In this particular system, in this particular simulation, you would trip 3 stages of under-frequency load shedding, and then you would come back and recover to 60 hertz. So this is one of the benefits of energy storage in an islanded power system. And hopefully you can see how critical energy storage is in a power system, especially as they move towards renewables. I think that's my last slide. Next? Yes. Okay.
I know you all want to eat lunch, but just a quick question.
I want to thank whoever put me right before lunch as opposed to right after.
It's better than being right after lunch.
I know.
But we have some excellent speakers as well, and they'll keep telling you how cheap the power will be, and that should keep you awake. Thank you so much for citing a lot of the challenges Hawaii is facing, because, I mean, as we all know here, island systems, no extension cords, we're the generator, we're the grid, we're customer service, fully integrated, fully siloed power company. So GPA has to solve multiple pieces for the community. So we are wrestling with this issue that, from what we hear a couple of different arguments on the solar piece in particular, and Hawaii. So on the one hand, we hear from you and others that Hawaii is or HECO has had to say timeout on on more permitted users because the grid has had some challenges. But there are very smart people in Hawaii on the solar generation side, and I think Stephen Chu, a Nobel laureate, former energy guy, who says all of us that don't think we can be 100% renewable are crazy. It's all done. Now, he talked about you don't have to worry about it until you get 20% penetration. Mr. Chu did. We know Hawaii has significant penetration in many of the islands. And what we're trying to avoid, as the head of the PUC for Hawaii said, was let's not argue about it. Let's figure it out. Let's gather and sit down and figure this out. So as you listen to this plan that we're hatching, we're saying we should grow renewable, particularly solar energy. But we're going to have to bring storage with it to help us manage that grid better and make sure the grid can handle the power that we're distributing to all sorts of people. You know, and yet we've got some folks that saying you can be 100% renewable by 2025. Could you just share us your views as a professional engineer? Just, you know, how real is this idea that you could be 100% solar, and how do you assess this approach GPA is taking to grow solar, have something else besides LNG? Because Hawaii even says what 40% by 2030. In 2030, 60% of the power is coming from something that's not renewable. So you got to think of something, whatever it is, and yet the grid's got to work. And what lessons learned would you offer to us Hawaii's a wonderful place. It's funny, at this last conference I was at, everybody got up and started beating up Hawaii, and the Hawaii lady had to get up and say, hey, Hawaii's a wonderful place. Hawaii's a wonderful place, and we can learn a lot from them. And we should learn a lot from them because the models are very similar. Can you just chat about how do we marry all these interests from the engineering point of view, and kind of what do you see, how realistic do you think Guam, or where do you think Guam could be with solar energy, or island communities with solar energy by 2030, 2040, as your sense of the technology and the maturation occurs?
Well, I think if you plan for it, there is a limit to how much generation you can put on your grid that is inverter-based. There is a technological limit. One of the things that currently, under the existing technology, a solar inverter provides about 10% more of its current energy to the power system during a fault, 10% more of its base-loaded or base-rated energy to the power system during a fault than it does, right? Conventional generation provides about 5 to 7 times its current during a fault for conventional generation. Well, what's important about that is that the power system is designed to operate under that fault current. Okay? So if you go to a renewable-based system, and I think it's important to say not just a renewable-based system, but an inverter-based renewable system, you have dropped your fault current availability by a factor of 5, right? 6. Well, what does that mean? That means if you have a fault on a line that your conventional relaying or your conventional fuses can't see it. You can't protect it. You don't know if the system's on the ground. Can you overcome that? Sure. I mean, I think from a technological point of view, you can plan to be renewable, 100% inverter-based renewable. Can you do it without planning? No. Can you just say, I'm going to put on 100% renewables and the system will work and the utility just needs to figure it out? They can't do it. The existing power system equipment is not designed to operate that way. That's not to say that you can't make it operate that way. That's just saying that today it doesn't. There's a few other things. I mean, Hawaii, the big island in Hawaii is about a little less than 60% renewable this year, if I understand my latest figures correctly. That's a huge accomplishment. 60% renewable, and they are very aggressive. I mean, Hawaii is very aggressive, but you need to make sure that you plan for your renewables that are going to be on your system and not react to the renewables that are put on your system. I think that's really what I'm trying to say is that, you know, you need to plan for it. If you want that level of renewables, fine, plan for it. You can't have that level of renewables without the planning associated with it. That's really my biggest issue is that there are a lot of issues with renewables that kind of get slid under the table because people don't want to deal with them. You know, fault current, for instance, means that how do you clear a fault, right? How do you start a motor? Fault current is what starts a motor. So if you have a system that has any kind of large motors on it and you drop your fault current by a factor of 5, how do you start the motor? Yeah, you can do it, but you need to figure out how to do it before, you know, you get there. There's a lot of those issues. You know, how do you resolve this issue of ride-through requirements? Ride-through requirements are the hugest issue that's facing the Hawaiian Islands today. You know, it's something that you need to get a hold of. So yeah, I mean, I think it's there. I think there's a lot of good things you can learn from Hawaii. You know, we do a lot of work in Hawaii. We run a lot of studies for them. We do a lot of work for mitigation plans and whatnot. So there's a lot of good things you can learn from.
Okay,
I have a quick question.
there you are.
Hi, Mr. Burlingame, Jonathan Diaz here, government researcher. I'm kind of, as a consumer of Guam, kind of bothered a little bit by this, that we've gone full steam ahead with the Dundun project at NRG Solar, which I actually thank Mr. Gassidier for making the presentation. Now that you're telling me this in terms of the energy storage, does GPA have a plan for the storage facility? And if so, where is this in the plan? Because I did not hear it in the morning. Kim, thank you.
Well, I guess first of all, you know, the Dandan project is a utility or a plant storage project or a plant solar project. So you can really define what its interconnection requirements and ride-through requirements are. So you can mitigate from a plant utility point of view, you can mitigate a lot of the problems that they see in Hawaii on the Dandan project. That's just an interconnection requirements issue. Now, you still have to deal with the regulation issue, but the interconnection requirements issue is very solvable with a plant storage system, and it's really not a big deal at all.
As to your question on not hearing it yet today and where is it at in the planning, John Cruz will be speaking this afternoon, 2 o'clock. I sure hope you'll stick around and you'll hear more on that subject.
And Zig, let me clarify for that question. By the way, we just have legislation now pending approval for a $94 million bond issue that Chairman Sanchez mentioned this morning, of which about 38 to 40 million of that 94 million is earmarked for a 40 megawatt battery storage system as a result of our system studies that EPS and Dave and Dr. Cody have completed. But I do have one question, Dave, and please bear with me. I know I asked you this question before, and please don't answer like from engineer to engineer, but for the audience's sake and the benefits of, I did ask you with the imminent retirements of many of our units that are being foreseen, and that knowing that, you know, the technology for flywheels that are so complicated and they're very high speed units, 30,000 RPMs, that sort of thing. But with conventional units, where we take a synchronous machine and you remove the fuel burning component of it, i.e. the turbine or the boiler, and convert the synchronous motors with the weight. I did ask you this question before. How can we leverage those types of systems as opposed to the very, very complicated modern technology for flywheels, and leverage existing assets we have here today on the ground as a flywheel technology? And I know we've dismissed it in our studies. I grant that, but because of such the high expense and the operating expenses. But maybe you can speak to the audience about my question to you many months ago when we engaged in your services to conduct this study. and that we ended up with batteries as opposed to flywheels. That was my question, and I'll shut up.
Okay. What Ken's referring to is that when we talked about a flywheel is just a motor with a big weight on it that spins this weight. And what Ken's referring to is as they retire some of these generators, the generator would be, instead of just retiring the generator, they would disconnect the generator from the engine or from the turbine and let the generator spin on the power system. And as part of that, they would connect another weight on the generator, and it would essentially be a big motor. So you would have instead of having a couple of horsepower motor, you would have a 10 megawatt motor. And that is feasible. I mean, we didn't look at that in the study because, that's really, in my mind, that would really be used as a power quality type issue. It could be possibly used with regulation, but with that type of flywheel, that's really a quality issue, not a storage issue, so to speak. That type of installation is very common in mines. If you have there are several if you have a large, like a drag bucket, on a big mine or something, almost all of those have a flywheel on them. So that when you're dropping the bucket down, you're charging this big motor. When you're pulling it up, you're discharging the motor. All of those have a motor on them to try and not incur power quality penalties from the utility. And that's essentially what this would do. It would help the power system handle some of the fluctuations of solar and wind from a regulation point of view, from a short-term regulation point of view. But it wouldn't help the power system. One of the hardest things for an islanded power system to deal with in terms of regulation is not necessarily the really fast changes in solar and wind. It's a long ramp down event. So in a long ramp down event, your inertia out of that type of machine without any auxiliary controls is fairly limited because it's a very slow response. So an inertia like that, an inertia draw from that requires a very rapid change in the power system frequency in order to work. In the flywheel technologies that's with controls, you can do that. You can look at a long ramp down event and you can say, I'm going to artificially draw power out of the flywheel. But if the flywheel is directly connected to the power system, then you can't do that. I hope that answers your question.
Okay. John?
Other frequency issues on a system, and should be of some battery units to those locations that have
Under voltage problem? Yeah, there could be some benefit for the batteries using a distributed battery system for under voltage. That may become more important as distributed PV becomes more prevalent. In our study, we didn't see that requirement as a need necessarily because we didn't see a real undervoltage problem on the GPA system. But as your distributed PV portfolio changes, or if you see an increase from what we studied, distributed batteries may be a requirement. But that's at an increased cost, right? So.
Okay, any other questions? Okay. Thank you, David.